So the professor has given us the question here. We can see at the equation here, both equation 1 and 2. The first one is equation 1 that tells us yt equal to beta 0, and then xt beta plus ut, and t from 1 to t, which tells us that it is a time series problem, right? And we also know from the equation 2 that xt equal to v0 and then z1 v1 then plus z2 v2 plus vt. And from the problem also we know the distribution of z1, z2, ut and vt. They are IID with mean equal to 0. Then standard deviation are omega here. And we know that the matrix of omega here is like almost equal to identity matrix. But for element, the third and the third element, we have like sort of problem here, 0.8. I mean, that could tell us that we have endogeneity problem here. And also we know from the problem here that we have the parameter beta 0, beta and phi0 is equal to 1, and the x1 is defined as the factor of 1, which the number of rows is t. So basically we have to, based on the explanation from professor before that, we have to just, and we pay attention to how to generate the data on z1, z2, ut and vt here. And we can look at the z and beta, and let's move to r, I guess. Let me focus just with the function here, because I have defined the function here, and that we have to define a function with arguments here. I put phi1, phi2, and t. Why? Because based on the question, they are only ask for different phi1, phi2, and t, right? Let's see the question point 3. We have phi1 5, phi2 10, and then t equal to 50 and 500. And question 4, we just changed the value of phi1 and phi2 actually. So that's why I put the parameters here for the function. Only just change the phi1, phi2, so we sort of minimizing the time of running the problem here. And then based on the problem, we have to define beta 0, beta and phi0. All of them are equal to 1. And also we have to define the number of repetition, which equals to 1000 here. And just ignore this one for now. Yeah, the x we just have to ignore first. And then we have a factor of mu, which all of them are equal to 0, and omega, just like in the equation. I have like defined the matrix here exactly the same with the problem. And also I tried to make a data frame or just a table here in order to put all of the parameters that is resulted from the repetition. So in the table here I just define 5 columns, with the first one for the beta OLS, because we sort of make 2 equations here, right? The equation for OLS and the equation of 2SLS. So just it's not problem chunk, right, with R. And why we use rep here, because we sort of repeat the value of 0 until the number of repetition. So let's say R is 1000 here. So basically we provide with the value for all of the columns here. The value are zeros, and how many? There are as many as R, which in here is 1000. All of them here. Why we should provide this? Because programming language sort of thinking how to efficiently store our objects, in which in this case the vectors. So we have to define the vector first with the number of rows are equal to what sort of how many of number that we have to put in here. That is why R here. And then at the end of the day, this guy will will replace the value of this guy, right? And this statistic here will also replace here, and the same with 2SLS. And then also G stat here, because we are also asked how to define the G stat. If we open the material from Professor Firmin, we can see the G stat is actually n times the Qn. Yeah, Qn. Qn like the equation of the IV, and times the matrix of Z prime Z over n, take the inverse, and take and then multiply it again with the yt minus xt beta times z. That's one. You can also see from the hint, but in the slide actually it's actually provided. So here is the main part of our problem here. Just like before, we have to provide the repetition, which in this case 1 to r, and don't forget with the set seed again in order to generate the different random numbers. And for the data generating process, I use this because we have multivariate here, right? And with the number of n here equal to t, which in this case the first one is 50, and mu, we take the factor of mu, which we define here, all of them are zeros, and the sigma, we take the omega. And for each variable z1, z2, u, and v, we just take, because here we result we have the result in form of matrix, and in order to get the value of z variable z, z1, z2, u, and v, we have to take each column. I mean, the first column correspond to z, the second column correspond to z2, and so on after until we have v here. So in order to continue with the our LM model, we have to put all of the vector here in form of data frame. So we put them in data frame. We put x equal to x that we have. We haven't defined x, I guess. Let's see. Oh, the first x is actually repetition of 1 until 50, but we later on we will replace that x with the x that we have we resulted from the second equation. And here is the data generating process for x, which it is nothing but the second equation actually, v0 z1 times v1 and z2 times v2 plus v. And again, I have to provide this vector x into the data frame. I just replace the first x with the value of x that is resulted from the data generating process here. And also again, we need to generate the values for y. So we get the value of y here based on data generating process from the first equation. And we've got the value of y here, and then we have to provide it into the data frame again, right? So our next step is to run the OLS model here. We call the OLS model here. We run our linear model with our dependent variable y and independent variable is x, because in the question here we are asked to generate the value of t for beta for OLS and t for LS, and then t and beta both for 2SLS and G stat. In here, first we define the OLS model, which take the equation in the first equation, and then we generate all of the coefficient that we have got into we put them into the vector that we have we have defined before. And for second model, we have 2SLS model here, and we have to go through the two steps. The first one is we have to define the regression model based on the second equation, which is the first step here, right? Yeah, so we regress x on z1 and z2, and then we take the estimated value of x, which I put here x underscore hat, just to differentiate with the previous x. So again, I take the value of x hat here and then put it into the data frame that we have defined before in order to be called into the next model. The fitted values is actually, we just take the predicted value, which is x hat here. So if you run through the OLS model in R, and then you just call the name of your model, and then the dollar sign, and you call fitted values, it will give you the x hat actually, just like residuals. When you call residual, just put residuals and it gives you the residual of the model. And then now I define the second step here, and I call it model step 2, just to differentiate it with the first model. Yeah, so I call LM again, but instead of taking the x, I take the x hat here that is resulted from the first step. So we basically just regress x hat to y here, right? And the data frame name is the f that we have defined before. And the process is the same, but just the name is different here. Instead of taking the slope OLS, I put slope to SLS here. Yeah. And then next we are going to compute the Sargan's G-stat here. Sargan formula here. We have to take the inverse of the matrix Z prime, and then multiply a dot product with the Z itself and divide it by T, and we take the inverse. So in R, if you want to calculate the inverse, we just take solve here. You can take detailed attention here. It is the Z that we have defined in the question also. So here we just define it into code. 1 over T dot or multiplied by the transport of matrix Z and dot the Z itself. It is we are going to take the weighting matrix here, and then we can put the weighting matrix into the equation. I'm actually the annihilator, and again, because Qn is defined by let's take this one. Can you see the thing that I highlight here? Yeah, Qn is actually this matrix Uy minus x prime beta multiplied by Z, and we multiply it with the Wt matrix that we have got here, and multiply it again with this one. The first one we take the prime and then multiply it by this one, and then again we multiply it here. And in form of the code here, let's see here. I take this matrix here. M matrix here is basically M is actually I just want to simplify the problem here. Basically, it is from this one. In terms of the code here, first I define the model here, and then I take the residual, and then that's what we got here. And then next we should multiply this by Z, which is Z here from the Z that we defined, the matrix Z, x1 and then z1 and z2, right, for the instrumental variables. Yeah, so we just actually multiply the residual with the instrumental variable to get the Qt. Qt is the equation that we want to compute the G. So Qt here is y minus xi prime beta. It is transpose and then multiplied by Z, and we take the product with Wt, and again we multiply it by itself. So basically this equation is like this: Qt equal to y minus x prime times beta, and then take the prime and multiply by Wt, which is the matrix of weighting matrix here, Sargan weighting matrix, and then we multiply it again with itself, y minus x prime beta. So next we are going to calculate the G-stat here. With the formula is like this: G-stat equal to T. So T, which is basically here n in the slide, and we multiplied it with Qt. And don't mind the index 1 here, because Qt resulted in a matrix, but the matrix is only only has one element. So in order just to take the scalar, I have to provide the index here, which is nothing but 1.1 here, 1,1. This matrix, if you want to take the transpose matrix. So far we have got the beta estimate for OLS, we have got T for OLS, we have got beta for 2SLS, we have also got the T for 2LS, and we have got the G-stat. And all of that are the requirement parameters in order to continue with the problems, right? So again, I put all of the parameters values in this table, statistic table, which nothing but what we have defined before. That is why the value 0 here, we want to replace all of them with the value that we generate from the estimate. So again, we return the data frame here, and that's it. We've got what is required for problem number 1. And then because I took the default value for the function is like v equal to 5 and v2 equal to 10 and t equal to 50, which is nothing but for question number 3. So I put the default value for the function for equation number 3 here. So even though I don't provide any value here, my code has understood that is my default value, so I just need to call it. It provided with the data one, yeah, this one. So we've got what are required. We've got beta for OLS. We can inspect here. We have 1000, which is based on the repetition, right? So we've got the question number 1 here, and then don't mind this because it's only to inspect the problem. And then let me run function that I have defined for histograms. I think it is not different from our previous case. It is basically just calling the histogram, but because I want to like provide 2 histograms at the same time, so I have to provide here the function called bar. And it is the argument is 1.2, which means that I have to provide in a graph, call it like 2 histogram and put it side by side. And here the histogram of beta OLS that you can see here. And again, I also put the default value for t just like before, equal to 50. And don't mind the color, you can pick any color that you want. And then the next histogram here is for beta 2LS, so I want to put side by side the histogram of beta OLS and beta 2SLS here, so we can just compare it easily. And then let's run this, and next we are going to see the plot for just like before, but here I put the 3 histograms like side by side instead of 2. And again, the data we are going to provide next is the data that we have degenerated from the first function. And again, here it takes t start OLS, and the second histogram is t start 2SLS, and the third one is g start. So we put all of them side by side. And then for the next function here, we are asked to provide the bias. First, we define the bias for the OLS, which is beta OLS minus beta here, and take the average. The bias for IV, just the same. We basically take the average of the deviation from beta to LS with the parameter beta. Here in point C, we are asked to provide the bias for both OLS and 2SLS. So in this function, I just provide a bias here, so we can just put them side by side and we can compare. So again, we put them into data frame. For the last one, we are also asked to provide the rejection frequency, and here we are providing one additional column for rejection of OLS. And again, we compare it with the value of t, which is by default here it takes the value 1.96, which is the t value for alpha equal to 5%, two-sided. And the same for rejection for IV. What different here is the rejection rate for G start, because it is chi-square. Chi-square 1 is actually equal to 3.84 for 5%. We are consistent with 5%. How do you know that? We can basically call it with R. Yeah, so 0.95. It is the code for R actually. And then we provide the degree of freedom here with 1. That's it, 3.85. But I think it's also mentioned in the equation, right? Yeah. But the same, if you want to calculate yourself, it is the code. And again, if it fulfills the criteria, we put 1, and except if we don't fulfill the criteria, we put 0. And then later on, we can calculate the average of rejection rate. So here, we have rejection for OLS. We have rejection rate for IV, and the last one, rejection for G start. And we provide all of them into data frame, so we can call them like at the same time. Let me call this, no error. Let's see the plot of beta based on the function that we have defined above, right? So let's see how it works with the plot betas. So it gives us the results here that we can see here. We can see here the histogram for beta. The first on the left hand side of the screen, it is the beta for OLS, and on the right side is the beta for IV. And we can see here the two are almost equal, right? That they are centered at 1, which is the value of our parameter. So we can basically interpret this that the resulted beta with both are centered at 1. And then we can look at the plot for T and G start here. We can just call it just like before, and then we get it here. And you can expect here that for the third, it's not normally distributed, but chi-square distribution here. Yeah, G test, because it doesn't. Alright, so you can tell a story based on these graphs.